Good evening. My name is Alain Gorielli and I'm in charge of external relations for the Mathematical Institute. Tonight, for the Oxford Mathematics Public Lectures, we have a very special event. But before we proceed, a special thanks to our sponsor, XTX Markets. XTX Markets are a leading quantitative-driven electronic market maker with offices in London, Singapore and New York. Their ongoing support is crucial in providing you with quality content. Now, it is usual to say that a particularly prestigious speaker does not need an introduction. This is especially true for Roger Penrose, co-winner of the 2020 Nobel Prize in Physics for his work on black holes. Tonight, we will join the celebration and explore his work and life in details. The event will have three parts, revolving around Roger, black holes, and singularities. As Sherlock Holmes once said, singularity is almost invariably a clue, and much of Roger's work follows that clue. First, we will hear from Dennis Lehmkuhl from the University of Bonn. He will introduce the general concept of space-time, singularities, and black holes, and place Roger's work in its historical context. Second, we will hear directly from Roger about his own work. As you probably know, Roger is also an extremely talented public speaker, and I've always enjoyed his lectures. Finally, the lectures will be followed by an interview with Roger by Melvyn Bragg. Melvyn Bragg does not need an introduction either, as you probably have listened to his wonderful BBC radio program In Our Time. On a personal note, I've had the great pleasure and privilege to interact with Roger at the Mathematical Institute. I would like to echo the voices of many in the Institute and say that, of course, I've always been impressed by his brilliant intellect, but also by his warmth as a human being. So, one more time, congratulations, Roger, and I very much look forward to tonight's event. Dennis, please start now.
Spacetime singularities are among the most fascinating ideas in the history of science. They are also among the most puzzling. For what are they? Are they objects that could actually exist in nature? Or are they artifacts of our mathematical reasoning? And how are they related to black holes? At different points in the history of general relativity, or GR for short, different answers to these questions have been given. A major milestone of this story was Roger Penrose's singularity theorem of 1965, which changed our entire thinking about spacetime singularities and indeed our thinking about GR more generally. The purpose of this lecture will be to put this theorem into its historical context and to prepare you for Sir Roger's own lecture on how he found the theorem and on how his thoughts on the topic have developed since then. Everything starts with three questions. The first question is, how does gravity work? And in 1915, Albert Einstein gave an entirely new answer to this question. In 1920, Arthur Eddington answered the question, how do stars work? And the two questions together, as they developed over the next decades, brought about a third question, which was answered in the work of Roger Penrose. Does the gravitational collapse of stars lead to singularities in spacetime? Now, how did all that happen? Here's a snapshot of Roger's paper from 1965, which bears the title Gravitational Collapse and Spacetime Singularities. In the next half hour, I will try to show you how these phenomena became related. And here are a few sentences from the introduction. Do not worry if not everything becomes clear immediately. It's the purpose of this lecture to help with that. So here goes. Most exact calculations concerned with the implications of gravitational collapse have employed the simplifying assumption of spherical symmetry. The general situation with regard to a spherically symmetric body is well known. When sufficient thermal energy has been radiated away, the body contracts and continues to contract until a physical singularity is encountered at the center of the body. As measured by local co-moving observers, the body passes within its Schwarzschild radius. The question has been raised whether this singularity is, in fact, simply a property of the high symmetry assumed. It will be shown that deviations from spherical symmetry cannot prevent spacetime singularities from arising. And what we're going to do in the next half hour is to essentially introduce the core concepts of these claims and to make it visible how much of a game changer the result at the end really was. So we're going to talk about the notion of gravitational collapse and how it's related to spherical symmetry, which was a major assumption in earlier work on gravitational collapse by Oppenheimer and Snyder, criticized by Wheeler, and referred to by Penrose in this footnote number 2. We're going to discuss about different notions of singularities, clarify what a Schwarzschild radius is, connected to the so-called Schwarzschild singularity, and we're going to put into a wider context why it was such a game-changing result that deviations from spherical symmetry cannot prevent spacetime singularities from arising. Now, to start with, here is the general structure of Penrose's singularity theorem. And indeed, Penrose's theorem served as a blueprint for all later singularity theorems and completely changed how physics thinks of what a singularity actually is, and whether accepting GR means that you have to accept the existence of singularities in spacetime. Here's the structure of the 1965 theorem in particular. And I'm going to argue that almost every part of it put what came before it on its head. There's the first assumption, which says that local energy is non-negative. And we're going to see that this is a far more general assumption than any assumption of collapsing matter that had come beforehand. I'm going to talk in detail about the newly introduced concept of a trapped surface and why it really changed so much in the history of GR. And even the conclusion that incomplete geodesics will follow from these conditions and bring about a singularity in spacetime was new because it was a new way of thinking about what a singularity really is, as we're going to see. But to appreciate how radical these changes were, how much of a game changer the first singularity theorem actually was, we have to understand what came beforehand. We have to understand how we got from Einstein's derivation of the perihelion of Mercury to that of Schwarzschild singularity, from there to Hadamard's catastrophe and Einstein's argument that the catastrophe would never ever happen. And we have to understand Oppenheimer's and Snyder's thoughts on the gravitational collapse of a star before we can understand the significance of Penrose's newly introduced concept of a trapped surface in spacetime and what follows from it. Now, we're going to structure the whole thing by looking at the 3 questions I mentioned at the beginning. First, how gravity works, how stars work, and whether they might be able to collapse. And finally, this will point us to the question of what a spacetime singularity is and whether it's linked to gravitational collapse and the existence of black holes. Okay, first, the question, how does gravity work? The whole thing starts in 1915, when Albert Einstein introduced what we today call the Einstein field equations, the new gravitational law that was supposed to replace Newton's gravitational law from hundreds of years before. The equation links the gravitational field on the left-hand side, associated with the curvature of spacetime, and the mass energy of matter on the right-hand side. Essentially, the equation says that the more mass and energy you have in a given region of spacetime, and depending on what form and shape that mass and energy has, will create a particular gravitational field, a particular curvature of spacetime in that region. Now, here are the 2 equations again. The full Einstein equations with a mass energy of matter as a source, and the special case when no matter is present, and when you have a pure gravitational field, which is described by solutions to this equation. In fact, every solution to these equations represents a universe or a part of the universe that is possible according to GR. And in 1915, in the same month in which he found the field equations, Einstein set out to describe a particularly important part of our universe. Namely, he wanted to derive the path of Mercury around the Sun. That's a problem that had caused some trouble for Newtonian gravitational theory, and Einstein thought that his newly introduced theory of gravity should be able to do better. And in setting about to solve this problem, he took the linearized vacuum equations. Linearized because he knew that the gravitational field of the Sun was comparatively weak, and so he could use the linearized equations. He was also only interested in the exterior gravitational field of the Sun, not in the Sun itself, and so he took a solution to the vacuum equations. The sun itself did not need to be modeled in order to know how its gravitational field influences Mercury. This is going to be important. He further made 3 assumptions about the gravitational field that the sun would produce. First, he assumed that the field would be spherically symmetric because the sun itself is approximately spherically symmetric. Second, that the gravitational field would be static because the sun is approximately static. Doesn't change very much, at least as far as Mercury is concerned. And third, that the gravitational field would be asymptotically flat, that far away from the sun, the curvature of space-time would tend towards flatness because the gravitational field becomes weak. Now, Einstein did not really expect that an exact solution to his complicated equations would be possible, and the approximate solution was good enough to give a precise calculation of Mercury's path. But only a few months later, Karl Schwarzschild, an astronomer, found the exact counterpart to Einstein's 1915 approximate solution. And you see the solution down here. Every solution of the Einstein equations gives an interval that is formed by the metric tensor, which gives the distance between any 2 points in spacetime. And Schwarzschild's solution had 2 surprising properties. Well, at least one surprising property. It had a singularity in the center, and that central singularity was not quite unexpected. The spherically symmetric solution to Newton's gravitational equations had a singularity at its center too, a point where the gravitational field, or the components of the metric tensor, tend towards infinity. Schwarzschild and Einstein interpreted this singularity as a placeholder for the sun that had not been included in the model. But there was also a second singularity, and that came as a bit of a surprise. Because it had a ring-like shape. So you see here is the central singularity, and here is the ring-shaped second singularity that has no counterpart in Newtonian gravitational theory. Both Einstein and Schwarzschild were a bit puzzled about this, but Schwarzschild eventually convinced the two of them that it wouldn't really be a problem, because for any realistic star, that ring-shaped singularity would be inside of the star, not really accessible to any possible measurements. So there was no real problem without what I would call the central singularity. It was the so-called Schwarzschild singularity, not by Schwarzschild, but soon by others, so-called, with its ring shape that puzzled everybody. And discussions about the nature of the Schwarzschild singularity came to a head in April 1922, when Einstein gave a series of lectures at the Collège de France in Paris. So you see him here discussing something that looks pretty similar to what I just said on the previous slide. 2 rings that might well be, one of them, the outer surface of the sun, and the second, the Schwarzschild singularity with its ring shape. Now, at this conference on the 5th of April 1922, Jacques Hadamard, great French mathematician, asked Einstein, what if a star were to be so massive that its Schwarzschild singularity ended up outside of the star? And Einstein immediately answered, this would be a catastrophe for the theory. Now, only 2 days later, Einstein came back and said, well, Hadamard's catastrophe will never ever happen. I've calculated that before a star could accumulate sufficient mass to be entirely contained within its own Schwarzschild radius, the pressure at the center of the star would become infinite. Under such conditions, he said, clocks would not run, and thus time would stop, preventing the Hadamard catastrophe from ever developing, since nothing develops without time. Now, why would it have been a catastrophe in the first place? Einstein was fine with introducing singularities to stand in for matter, like the sun, as long as singularities could be interpreted as a placeholder for matter rather than something that actually exists. Everything was fine for Einstein. That's why he did not worry about the central singularity in the Schwarzschild solution. But singularities were not supposed to actually appear in nature, and that's what was at stake in the debate with Hadamard. Hadamard asked if a star could be so heavy that its Schwarzschild singularity would be outside of the star and actually appear in empty space. Now, discussion during the 1920s kept focusing on the nature of the Schwarzschild singularity and how it should be interpreted. Here's a quote from Arthur Eddington from 1920. He said about the Schwarzschild singularity, there is a magic circle which no measurement can bring us inside. It is not unnatural that we should picture something obstructing our closer approach and say that a particle of matter is filling up the interior. So for Eddington, it seemed like a barrier. And other names introduced in the 1920s, there was a real cottage industry introducing ever new names for the Schwarzschild singularity, went in the same direction. Schwarzschild himself called it the discontinuity. Kotler called it the barrier. Weil called it sometimes the sphere, sometimes the gravitational radius. Reichenbecher called it the hole in the world, quite prophetic, given that, as we will see, the Schwarzschild singularity will eventually be related to the event horizons of black holes. Briolin called it the singular frontier, the catastrophic frontier, the limit circle, and Nordmann, the person who took the notes at the Paris meeting, simply called it the death. Now, I've not seen anybody comment on this, but it's a bit surprising, it's a bit ironic that the person who introduced, to discover the Schwarzschild solution and the Schwarzschild singularity, that would eventually be related to the event horizon of black holes, was Karl Schwarzschild, who, if you translate his name into English, the name would mean black shield. Accident of history. All right, so much for now about the development of the theory of gravity in the 1910s and the 1920s. Now let's turn to our second question. How do stars work? And the first promising answer to this question was given by Arthur Eddington in 1920. Eddington suggested that stars shine because of the energy produced in the nuclear fusion of hydrogen. The resulting outward radiation pressure is what keeps the star from gravitationally collapsing. Because if there was no pressure to the outside, then an object as heavy as a star would simply collapse under its own gravitational attraction, under the gravitational attraction of its parts. But this immediately created the question, what would happen when the star runs out of hydrogen to burn, and thus out of the fuel that makes the radiation pressure to the outside happen? Then only the inward gravitational attraction would remain. Would the star collapse? And if so, would he find a new equilibrium state, become a smaller star, less bright, but still stable? Well, in 1935, Chandrasekhar calculated for the special case of a neutron star, the kind of star that in principle could become the smallest possible star, that if a neutron star is heavier than a particular limit, there will be no new equilibrium state. And this suggested that the star would just continue collapsing to ever smaller regions of space-time. This line of thought was further strengthened by a calculation of Oppenheimer and Snyder in 1939, who called their paper on continued gravitational contraction. Oppenheimer and Snyder constructed an explicit, spherically symmetric model of a collapsing star. They predicted it to collapse continuously without ever achieving a new equilibrium condition, collapse to within the ring formed by its Schwarzschild singularity. They also predicted that once this happened, what lies within the boundary formed by the Schwarzschild singularity would not be accessible to an outside observer anymore, and the outside would not be accessible to the observer within the boundary formed by the Schwarzschild singularity. In short, they predicted a collapsing star to turn into an object that would soon be called a black hole. And they predicted that as a result of this collapse, the central singularity of the Schwarzschild solution would form. So if Oppenheimer and Snyder are correct, then what Einstein and Schwarzschild thought of as a placeholder for matter could actually come about in nature. Now, did Oppenheimer and Snyder falsify Einstein's reasoning of 1922? I think not, because Oppenheimer and Snyder make idealizing assumptions that the pressure inside the star vanishes, whereas for Einstein, the assumption of a non-vanishing pressure played a major role in his argument. Thus, Oppenheimer's and Snyder's analysis rests on two very specific assumptions: that the gravitational field of the collapsing star is exactly spherically symmetric, and that the matter that the star is made of can be idealized as pressureless dust. Now, as we're going to see, Penrose would show that the major results of Oppenheimer and Snyder, that of continuing collapse and that of a formation of a central singularity, do not depend on these assumptions. This brings us to our third topic, where gravitational collapse and singularities come together. Relativists analyzed the Schwarzschild solution by using ever-new coordinate systems. Some of them got rid of the puzzling and now famous Schwarzschild singularity, and in them it looked like a completely normal part of spacetime. Such coordinate systems were found by Eddington in the 1920s, Lemaitre and Robertson in the 1930s, and by David Finkelstein in the 1950s. But the interpretation of these coordinate systems remained controversial, and knowledge of them did not really catch on. Even when Finkelstein rediscovered Eddington's coordinate system in 1956, many still spoke of the Schwarzschild singularity. Now, shortly before Finkelstein had published on his coordinate system, John Wheeler had entered the study of GR. Remember that Wheeler's paper was cited next to that of Oppenheimer and Snyder in Penrose's opening paragraph. Wheeler was a nuclear physicist and was lured into GR by studying the work of Oppenheimer's group from the 1951 onwards. Wheeler, Harrison, and Vacano reconsidered Oppenheimer's Snyder in 1957, using some of the earliest computers to model the gravitational collapse of a star. Way into the 1960s, Wheeler was very skeptical of Oppenheimer and Snyder's prediction of continued collapse. He expected that general relativity was not trustworthy beyond the Schwarzschild singularity and would need to be replaced by a quantum theory of gravity yet to be found. Still, it was Wheeler who made the term black hole stick for the type of object that Oppenheimer and Snyder had described, and who spent decades of his life researching the physics of black holes. Now, also in the early 1960s, the Russian School of Relativity took aim at the central singularity that Oppenheimer and Snyder had claimed would form. They wrote a paper, Tseldovich, and in particular Lifshitz and Kalatnikov, wrote a paper that argued that Oppenheimer's and Snyder's analysis of gravitational collapse is not generic, and in particular that if you did not have perfect spherical symmetry of the collapsing matter, a central singularity would not form. And that suggested that the fact that the central singularity did form in Oppenheimer's and Snyder's analysis was an artifact, a mathematical artifact produced by the assumption of spherical symmetry. Now, so far everything I've said was mostly about theoretical GR and how gravitational collapse could in principle happen to a star. There was so far, no relationship to any heavenly bodies. This all changed in 1962 and became clear, especially in 1963, at the first Texas conference, which brought together mathematical relativists and astrophysicists, because quasars had just been discovered. Here's a picture of the quasar 3C273, the brightest quasar on the night sky. And a quasar is a fascinating object. A quasar can emit more energy than our entire Milky Way galaxy. Now you might ask, how could it be that these objects were only discovered in 1962 if they're so energetic? And the answer is because all that energy is emitted in the radio spectrum, and we don't see radio waves with our bare eyes, nor with our optical telescopes. And so radio telescopes had to be developed before quasars could be observed. And this picture of a quasar was discussed at the 1963 Texas conference. Here's a picture of the same quasar, the brightest one in the sky, from 2013 from Hubble. Much prettier picture. Now, how is all this related? The idea quickly came up that the source of all that energy put out by quasars could be the gravitational contraction of a star, the death of a star that produced an enormous outburst of energy. And, so suddenly, all the calculations by mathematical relativists about gravitational collapse became immediately relevant to astrophysics, and everybody was happy. Tommy Gold, at the after-dinner speech at the Texas conference, summarized up the spirit of the conference and said, everyone is pleased. The relativists who feel they are being appreciated, who are suddenly experts in a field they hardly knew existed, the astrophysicists for having enlarged their domain, their empire, by the annexation of another subject, general relativity. Roger Penrose was present at this conference and was inspired to revisit his thoughts on gravitational collapse and the formation of singularities from years before. especially in the light of new mathematical tools that he had developed in the meantime. Now, one can interpret Eddington, Lemaitre, and Robertson as having understood that the Schwarzschild singularity is not a real singularity, but a coordinate singularity, an artifact of the coordinate system chosen. But it took Finkelstein and Rindler to fully realize that though the Schwarzschild singularity might not actually be a singularity, it is something else. In 1956, Rindler called it an event horizon. He defined an event horizon as a boundary in spacetime which divides all events into two non-empty classes, those that have been, are, or will be observable by a given observer, and those that are forever outside a given observer's possible power of observation. For the Schwarzschild solution, this meant that no observer outside of what was formerly called the Schwarzschild singularity can observe what is going on inside, and no observer inside this event horizon can ever observe what is going on outside. Penrose understood all this, and he will tell you himself how Finkelstein and Rindler influenced his work. But in a way, all this meant that, though strange, the Schwarzschild singularity was not as big a problem as physicists had long thought it to be. In contrast, the central singularity of the Schwarzschild solution, that originally nobody was worried about, had become more and more threatening with Oppenheimer's and Snyder's analysis of gravitational collapse. For there it looked as if such a singularity could actually arise in nature, as the result of a physical process, namely gravitational contraction of a star. Wheeler, Zelovich, Lifshitz, and Kalatnikov had argued that this was an artifact of the spherical symmetry assumed by Oppenheimer and Snyder. And this is where Penrose's theorem entered the fray. We're now in a position to understand the project that Penrose outlines at the beginning of his 1965 paper. We've understood what came before, what kind of gravitational collapse had been envisaged, and how in the work of Oppenheimer and Snyder, and criticized by Wheeler, spherical symmetry played a major role. And especially how the spherical symmetry had been argued as being maybe responsible for a physical singularity being produced at the center of the body, according to Oppenheimer and Snyder. We've also spoken about the Schwarzschild radius, which used to be called the Schwarzschild singularity, but by now, when Penrose wrote, had been reconceptualized as an event horizon, especially by Rindler, even though that reconceptualization would only really catch on after the work of Penrose into the late 1960s. And we can also now appreciate why it would have been such a big deal, or why it was such a big deal, that deviations from spherical symmetry cannot prevent spacetime singularities from arising. Because that went entirely against the development that had been going on in the previous 20 years, when Wheeler, Lifshitz, Kalatnikov, everybody expected that the formation of a central singularity was only an artifact produced by the spherical symmetry assumption employed by Oppenheimer and Snyder. We are also now in a position to see that at least two of the premises and the concept used in the conclusion of Penrose's 1965 theorem were utterly game-changing. Regarding the first assumption, if you think back to what I said, all previous treatments of gravitational collapse had assumed a very specific model for the collapsing matter. Penrose only assumed that whatever the collapsing star is made of, whatever symmetries the matter has, and no matter whether it is subject to pressure or not, the only assumption needed is that its local energy is everywhere non-negative. It's an incredibly minimal assumption about the matter concerned. Translated into a condition on the curvature tensor, this brings about a focusing of infalling light rays, and Roger himself will talk more about this. Now, the concept of a trapped surface that is introduced in the third premise was truly revolutionary, for it was one of the first global concepts in GR, and it managed to ship around all the previous problems involving coordinate systems and symmetries. I will say more about what it is in a moment. Finally, you've seen that previously, whenever anybody talked about a singularity, what they referred to was that the metric tensor or the curvature tensor would tend towards infinity. The problem was that you could never really be sure whether this behavior was because of the coordinate system chosen or whether it reflected something deeper. The idea of moving away from thinking about whether the metric or the curvature tensor becomes infinite and towards thinking instead about whether the path of a light ray is complete or instead suddenly stops, which is the incomplete geodesic referred to here. And to take this as a sufficient criterion for there to be a singularity was another game changer. Now, it is today hard to fully appreciate the ingenuity that the concept of a trapped surface demanded at the time. Note that it needed a coordinate system like that of Eddington and Finkelstein to be brought about, and yet the concept itself does not need any reference to a coordinate system, and it does not rely on the spacetime having any symmetries. It boldly allows for a global property of spacetime, while the consensus for half a century had been that only local concepts are to be trusted. That had been the whole push towards GR, away from Newtonian theory. So here's the basic concept, basic idea of a trapped surface. After the star has collapsed within its Schwarzschild radius, which has now been understood to not be a singularity, a sphere can be found in the empty regions surrounding the collapsing matter. And the sphere is an example of a trapped surface. Light rays, which means that light rays emitted from within the sphere, no matter in which direction they are shot, will always converge inwards. And here is Penrose's conclusion from the 1965 theorem about how trapped surfaces and singularities are related. He says, the existence of a trapped surface implies, irrespective of symmetry, that singularities necessarily develop. And the singular behavior that he speaks of here is exactly that the path of light rays cannot be extended further, that it suddenly stops. In the case of the Schwarzschild spacetime, this happens exactly at the center. So if this is the trapped surface, light rays are emitted somewhere here, they will all converge inwards towards the singularity, where their path suddenly stops. And this is taken as a sufficient criterion for the presence of a singularity. In the case of the Schwarzschild solution, the outermost trapped surface is located at the Schwarzschild radius, i.e. at the event horizon. Thus, what Einstein and Schwarzschild thought of as the Schwarzschild singularity is actually something entirely different. It's now been reconceptualized as an event horizon, something very different from a singularity, and a concept that had not been available to Einstein and Schwarzschild. Okay. So Einstein and Schwarzschild had thought of the center of the Schwarzschild solution as harmless, of the central singularity of the Schwarzschild solution as harmless, a placeholder for the star itself. But Penrose showed that for a collapsing star, and without making any assumptions about the symmetry of the star, about what it consists of, a singularity like this will actually arise in nature. If GR is right, then such a singularity is not just a mathematical placeholder, but something that could actually exist in nature. It would come into existence as the result of collapsing matter in the formation of a black hole. Now, and this was brought about by Roger Penrose's work. But what about Einstein's anti-singularity argument, his argument against the Hadamard catastrophe? Well, remember that Einstein's argument went against the possibility that the Schwarzschild singularity could ever end up outside of a star. Oppenheimer and Snyder showed that this is possible, and thus that black holes are possible. But Finkelstein, Rindler, and Penrose showed that the Schwarzschild singularity is not a singularity, but an event horizon. Now, would Einstein be reconciled by this? I think not. For the central singularity to appear in nature would have been equally catastrophic for him, now that it can't be interpreted as a placeholder for matter, but must be seen as the result of collapsing matter, and something that actually appears in the universe. And what about Wheeler's skepticism about space-time singularities appearing in nature? Does the existence of black holes necessitate the existence of space-time singularities? Well, yes, if GR is trustworthy all the way down into a black hole. Penrose's singularity theorem shows that singularities are an inescapable consequence of GR, and that they will inescapably form in gravitational collapse as described by GR. But as Roger would be the first to admit, and indeed did admit already in the 1965 paper, Wheeler's dream of complementing classical GR with a quantum theory of gravity that kicks in beyond the event horizon and might stop singularities from happening, from coming into existence, remains an open and viable project. Now, I would like to finish with two quotes. The first is a quote by Griffith and Podolsky on a textbook on the exact solutions of Einstein's equations. They wrote, it appears that it is much easier to find a new solution of Einstein's equations than it is to understand it. Well, and given, as we've seen, that it took Schwarzschild only a few months to find the Schwarzschild solution, and yet it took more than half a century to properly understand Schwarzschild's solution, which is the simplest exact solution of the Einstein equations, I think Griffith and Podolsky have a point. Here's a second quote, which is from Friedrich Hund. He's writing about the history of quantum mechanics, but I think the case applies here too. He writes, "How difficult were these advances? If we now acquaint ourselves with some of the detours, errors, and psychological blocks, it is not to console ourselves with the thought that even the great physicists do not always move in a straight line, but rather to grasp, in some measure, how difficult it really was." Well, this points us to the question, how did Roger Penrose actually come up with the singularity theorem and all the new concepts and ideas that went into the singularity theorem? If you think back towards the last half hour, you'll see that I haven't really told you how he came up with it. I only told you what was there before and showed you how all these concepts that he introduced put the entire state of the discipline on its head. Well, with that, I turn over to Sir Roger himself, who can tell you how he came up with the theorem and how his thoughts on the topic have developed since then. Thank you.
Well, this talk is sort of my Nobel lecture, but a little bit different. This first slide shows four-dimensional space. That is to say, I've got three space axes and a time axis. The idea of space-time was actually due to Minkowski rather than Einstein, but Einstein didn't like the idea when he first heard of it, but nevertheless, he got used to it, and then it was crucial to his theory of general relativity. Now, in the next slide, I'm going to show you what a light ray looks like. So we imagine a photon which is whizzing along with the speed of light. Now, in order that it shouldn't be just sort of in the spatial direction pretty well, I want to make the axes so that the speed of light is comparable in the two axes. So if the time is in seconds, then the space would be in light seconds. If it's years, then it would be light years. So it's 45 degrees or some reasonable angle. Okay, so that's a photon. Now, I'm really interested in the whole possible photon trajectories. That gives us the null cone. So the red there, you see the null cone, and I'm more interested in the null cone than in the particular light ray, because it really represents all light rays. So let's remove the light ray. In fact, I'm going to remove the axes. We don't need that. The crucial thing is the light cone. That's the most important structure in space-time. It's almost all the structure. I'll come to later what completes it to being all the structure, but it's almost all the structure. Now, in general relativity, in special relativity, the light cones would be all uniformly arranged. But in general relativity, where the space-time is curved, I've now represented it in this picture where looks like a surface, but you must imagine that the surface there is four-dimensional and that the cones also have another dimension to them, because the end of the cone looks like a circle or an ellipse. It really looks like a circle flattened out, but it really should be a sphere. So you've got to imagine, if you can, that the cone really has a sphere at each end of it. Okay, well, let's go on to the next picture. Now, the important thing about space-time is it represents the history of things. Now, if you have a particle which is moving with the speed of light, on the left-hand side, you see a massive particle. Its trajectory is always within the cones. It's traveling less than the speed of light, if you like. That's what that means. Whereas a photon travels with the speed of light, so it's always tangential to the cones. Now you see these little cones represent, usually I call them the null cones, but the light cone, if you like, imagine that a flash of light occurs at the little point P in the middle, just lower down the left. Suppose there's a flash of light there, then the light works its way out, and because the space-time is curved, it may do funny things later on. It starts out quite reasonably, but then it may start crossing itself. So you see at the top right-hand side, you see the light rays start crossing over, and we get what's called a caustic in the crossing region. And it's important that to realize that these things happen, because in the general space-time, light cones can behave in this sort of way. Okay, now let's move on. Now, I want to describe a little story here, because I first got interested in general relativity. Well, my brother told me a few things about it when I was young. And when I was an undergraduate, I bought a copy of Schrodinger's little book, Spacetime Structure, very nice little book where he described the ideas of general relativity. So I had some little bit of a feeling for the subject. And also a little bit later, I think when I was an undergraduate, I was listening to some lectures given by Fred Hoyle. I think there were 5 of them or something like this. And he was talking about, first of all, the Earth, and he went out to the solar system and further out. And then he started talking about cosmology. And he was describing the particular view of cosmology known as the steady state model. In the steady state model, you have the universe expanding all the time. The problem was at that time that there were 2 observations which seemed to contradict one another. One was certain clusters of stars called globular clusters, and they seem to be very, very ancient. And the age of the universe is calculated from certain stars called Cepheid variable stars, seem to say that it was actually less than the age of these globular clusters, which is a contradiction. How could the globular clusters be older than the universe? It was ultimately resolved because there was an error and people had looked at 2 different kinds of these Cepheid variable stars, and actually the universe was considerably older than people thought. But at the time, there was this apparent contradiction, so that the point of view known as the steady state model was put forward by Gould, Bondi, and Hoyle was describing this model in this lecture. So what we have here in this picture are the light cones in this model. In the central strip going upwards, that would be the part of the universe that we can see. You say this is us up here somewhere, and we're looking back. And the way Hoyle described it was that the galaxies get further and further away. They expand away from us. There's always hydrogen being produced to sort of keep the density of the universe constant. But the galaxies drift away, and when they get faster than light, then they disappear from view. That was what Hoyle said. And I found this very puzzling, because I drew pictures like this one here, and I imagined us looking back, and these cones sort of point outwards and outwards. And you see that our past, the light ray, as it follows the cones, will always intersect the world lines of the galaxy. So let me go to here. Here we see some galaxies. The world lines of the galaxies are always within the light cones. They don't travel faster than light locally, but you see, relative to us, they travel faster than light. And so Hoyle was arguing that they would disappear. And I thought, no, they don't disappear, because here's us at the top, and we look back, and our past light cone sort of creeps along inside this, well, the horizon, as we now call it. And we would always see any galaxy which had crossed across, you would still see it. It may fade out gradually and become fainter and fainter. That I did believe, but I didn't believe they just vanished. So I happened to be visiting my brother, who at that time was a graduate student in Cambridge. And I complained about this. I said I didn't see how the galaxies disappeared. And he said, well, I don't know much about cosmology, but over there is Dennis Sharma sitting at another table, and he'll explain it all to you. So I went and I talked to Dennis, and I gave him this argument. And he said, well, I'm not sure about that. And he went and said, I'll talk to Fred about it, Fred Hoyle. And the main point about this was that he realized that he thought that I would be good cosmology. When I went to Cambridge, I was actually studying pure mathematics. I was studying algebraic geometry, but Dennis decided he would teach me physics, and he thought that maybe he'd get some input from talking to me. He was very good at bringing people together. And at one point he suggested, this I think was a little bit later on, here we have the steady state model again. You can see our past light cone intersecting all the rays, the world lines of all the galaxies. Anyway, when I went back to Cambridge later on as a research fellow, I think it was, and I was at St. John's College, Cambridge, and Dennis suggested that I might accompany him to go to hear a lecture by David Finkelstein. That was at King's College, London in I think 1958. And David Finkelstein was describing basically, well, this picture here is the Oppenheimer-Snyder picture of a collapse to a black hole. See, at the bottom, we see material. You have to see time is always going up the picture in my pictures here. So here we have the bottom, some matter, which is considered to be sort of pressureless fluid, is the way Oppenheimer described it, Oppenheimer and Snyder. It was what they call dust, which has no pressure. Anyways, never mind. So it collapses inwards, and then you have this situation at the future where you have these light cones pointing in. Now, Finkelstein wasn't describing this particularly, but he was describing, look at the top part. This is a picture of the Schwarzschild solution. The Schwarzschild solution was introduced shortly after Einstein introduced his general theory of relativity. Karl Schwarzschild solved the equations for a spherical body, such as the sun, something like that, a star, say, and the way that the metric, the space-time metric, including the light cones, would behave was given by his equations. But the way he wrote the formula down, you came into a problem just at this place, which is the boundary, this sort of cylinder that you see going upwards. Its boundary where it becomes tangent to the light cones. In the coordinates that Schwarzschild was using, it looked as though it was singular. So you had a place where things go into infinity. Singular really means that something goes wrong, your metric seems to go to infinity, and that doesn't make any sense when that happens. So you give up at that point. But so people thought that the Schwarzschild singularity, which is this boundary, was a place where things blew up and you got nonsense. However, various people showed that by a change of coordinates, you could actually see that it wasn't a singularity, that you could, as long as you had a coordinate system which enabled you to describe these light cones pointing inwards. And David Finkelstein in his talk was describing, I think of the top part of this picture, forget about the collapse at the bottom. That was the picture that Finkelstein was describing. And I was very impressed by this because I really was most amazed by how you could get rid of this seeming singularity, and it wasn't there at all. Nevertheless, at the center, there you have this wiggly line in the middle, you really do get a singularity. This is where the space-time curvatures become infinite. And I came away from this lecture thinking that somehow you could manage to get rid of this thing you thought was a singularity, but you're still stuck with it. Maybe there's some general theorem which tells you whatever you do, you can't get rid of this nasty thing in the middle. I don't know quite why I thought you couldn't, but it seemed to me that somehow this was a problem. But maybe you have generalizations of this, which is not the spherically symmetrical case, with irregularities, and maybe the stuff falling in had a pressure or something like that, which might make a difference. A much more general situation, which is qualitatively similar, but not exactly the same. And do you still get the singularity, or do things sort of swish around and come swirling out again? And then I thought to myself, well, I don't know much about general relativity. If I was going to try and prove there's a theorem like this was about 1958, what do I do? Well, the only thing I knew that I thought might be unfamiliar to general relativity people at the time was about two-component spinors. I think a few months earlier, I'd been to a course due to Paul Dirac, the great quantum physicist, and this was his second lot of his, he had an elementary course and then a more advanced course, and this was in his more advanced course, and he deviated from his usual course, which was rather an unusual thing for him to do, and he described two-component spinors. I was trying to learn about them for other reasons previously. I just found them very puzzling and I didn't understand them at all. But Dirac's lectures made them very clear. And this is the sort of picture which I sort of, out of this, imagined myself. On the right-hand side, we see this little flag there. We have the future cone, and the flag pole is along the cone. So it really points out towards, as a light ray would go. You can imagine also in the past, so it point back along the light cone. So that if you look out at the sky, you're really looking at photons coming in from infinity, and these photons coming in would be a sphere. So this sphere on the left-hand side, like you can call the celestial sphere. If it's the past cone, that's the actual celestial sphere of light coming in, but we can still call it a celestial sphere of the light going out, so going out to infinity. And the little two-component spinner describes a single point on this celestial sphere. It's also got a little flag on it, and this characterizes the description of a two-component spinner. There's a little problem about the sign of it, which I won't go into at the moment. Okay, now what's that got to do with this? Well, not much, but I started thinking about this problem and seeing what I could do with general relativity. And I found that some things worked extraordinarily well if you wrote them in terms of these two-component spinners. You take the curvature of space-time, and it automatically splits into these two parts. One of them is called the Weyl part, and the other is the Ricci part. And the Ricci part is what Einstein's equations directly determine. So if you have a matter distribution, this matter distribution gives you the Ricci curvature. That is the Einstein equations. It just tells you that the Ricci curvature is given by the matter distribution. Trace-free, that really means you're looking at the light rays and not the whole thing, but never mind too much about that. But what the Ricci curvature does is to focus the light rays inwards in a sort of uniform way. It's like a positive lens, which magnifies things. So if the observer at the top here looks at, this would slightly magnify what he's looking at. Now, what does the Weyl curvature do? It distorts. So it's purely astigmatic. It's a lens which is entirely astigmatic, and it magnifies in one direction and minifies in the other direction. Anyway, I got a good, clear picture of how light rays were affected by the curvature. And at one point, I remember thinking about the steady state model. I was thinking about it, I think, at a time where it had sort of lost some credence, because people had, in the meantime, discovered the microwave background, which showed that the universe had an early stage in which it was extremely hot. So that this was more in accordance with the models of the universe, which expanded out from a Big Bang, whereas the steady state model didn't really agree with it at all. Now, Dennis, when he was convinced that these observations were correct, he changed his mind and he said, look, I was wrong to promote the steady state model. And I thought about it a bit myself, because various people were still going on trying to promote it. And I had a sort of thought, can you show that if the energy density is positive, that even if you wiggle, say, steady state model with wiggles in it, that can you have such a model? And I convinced myself, using focusing arguments, that you simply couldn't have one, that it would be an impossibility as long as the energy flux was non-negative. So this was something I had in the back of my mind. And later on, in the early 1960s, when quasars were observed, these are very, very bright things which initially people thought were stars. I think there were radio sources initially that they noticed, which were extremely bright, something like 100 or 1,000 times brighter than an entire galaxy. Yet they seemed to be pretty small because they varied in sort of the order of a week or so, which said that they couldn't be really bigger than the solar system. So how could they be that bright, have that much energy in them, and yet be so small? So various people did start wondering whether something like the Oppenheimer-Snyder collapse might actually be involved, and that you were looking at things maybe as matter gets smaller and smaller, it would produce a lot of energy, and that this energy might be a product of these things probing their Schwarzschild radius. I remember Fred Hoyle in particular was keen on ideas of this, of this sort, and it was certainly a strong possibility. But this made people think, what happens when stuff collapses? And they were thinking again about the Oppenheimer-Snyder collapse, which I just showed you a little while before here. The Oppenheimer-Snyder collapse. And here you get a singularity in the middle. But let's suppose that the matter falling in is very irregular. So it's a lot of irregular things swishing around in all directions. And maybe it just swirls around and comes swishing out again. And at this time, there were some papers. There was a paper by Lifshitz and Kalatnikov, two Russians, who seemed to show that in a general situation, we would not get singularities. And so I remember John Wheeler worrying about this a lot. And he asked me whether, can you give me insights into this? And I remember I looked at the Lifshitz-Kalatnikov paper, and I didn't find the arguments completely convincing. There actually was an error in the paper, which I didn't notice. I hadn't gone into it deeply enough to see that. But nevertheless, I thought it was worth thinking about the collapse problem anyway. And I remember walking in the woods and trying to think, was there some way I remember thinking that it had to be a non-local description, that you couldn't, because of the way things scale, it couldn't be something that was local and it just got too big and then it sort of swirled out again. It had to be some more global criterion. And at a certain point when I was talking to a colleague, and I had this idea came to me of how you could characterize a collapse which had reached a point of no return. Now, this is the Oppenheimer collapse picture, more or less. It's actually a picture from the paper that I drew. I drew the picture which describes, it was the paper which eventually got the Nobel Prize, apparently. And here we have a collapsing material at the bottom part of the picture. And as we go upwards, we see this little black ring going around it. You have to remember there's another dimension here, so that isn't really a ring, it's a surface. So, but you can picture it as a little ring going around, but it's a surface going around the collapsing material. And what's funny about it is that if you imagine a flash of light going all over that surface, that the flash of light converges on both sides. On the top right-hand picture here, you see a little bit of a surface, and you imagine a flash of light over that surface. On the concave side, it will converge, but on the convex side, it will diverge. What we have on a trapped surface is a situation where it converges on both sides. That looks a little strange. It's not actually all that strange in relativity. The bottom situation, we have two passed light cones, and as they intersect, you find a little bit of surface which has this property, it converges on both sides. But the thing about that is it's not closed up. It's not what's called compact. And what's funny about the picture here is that you have this surface which the light rays are converging all the way around, and it is compact. And it was that contradiction between that being a compact surface, well, really, it's the fact that you look at the future of that. So you remember I had this picture of the future of a point. Now, future of a surface is something a little bit more complicated than that, but the way that it behaves and the fact that it has light rays on it, which finally close up, and you could show that the boundary of that region, which is the future of that, what I call the trapped surface, that's the little ring in the middle there, that trapped surface had to be a compact region. And then you sort of project that backwards. I had a rather clumsy argument at the time. Charles Misner had a better way of describing it, which I hadn't thought of at the time. But the argument was, I was thinking of geodesics coming and hitting the initial surface. I should say the surface at the bottom is what's called a Cauchy surface. This is what people often do in physics. You consider at one moment, you say what everything is doing, and then your equations tell you what that stuff is doing later on. It's called a Cauchy surface. You have enough data on your initial surface to predict the future. Now, in this situation, I'm imagining a local thing, so the Cauchy surface could be assumed to be non-compact. It goes off to infinity in all directions. And when you project back your compact region at the top, which is the future of the trapped surface, the boundary of the future of the trapped surface, you simply arrive at a contradiction, and that contradiction, something is wrong. As long as the energy doesn't ever go negative, that would spoil the argument, but as long as it remains non-negative, you have this problem, and you get whatever definition you have of singularity makes a bit of difference, but you have something goes wrong, and this is the singular state. So what it's telling you is that you can't have a general collapse of the Oppenheimer-Snyder type, a body which is sort of reasonably compact in itself and can be very, very irregular. Actually can consist of a lot of stars. See, a lot of people used to worry, maybe in a realistic situation, could you avoid having a trapped surface? Do you necessarily have a trapped surface? Well, it's not so easy to see, so I often use a different argument. The same theorem applies. Suppose you have a point, the point at the bottom, they're called P, if you can see it, its future light cone, you can see it following up, and the boundary of its future, with this light ray start to converge again, that is necessarily going to be a contract region, and that's good enough. You don't have to have a trapped surface as long as you imagine that have a point where the future light cone of the light rays start to converge at some point. And it's not so hard to see that if you have a large cluster of stars, not say an individual star, the problem was people worried that if you have individual stars, the density might get so huge, and do you trust your equations when the density gets very large? But if you consider a collapsing collection of many, many stars, then it's very easy to see if you have enough of them. It's not hard. The density doesn't have to be, the average density can be less than the density of air. It's not much problem getting enough stars doing that. So it seemed to me that it was a very general phenomenon, and there's no problem about whether you can have a trapped surface. You could let this condition instead, just as the theorem works just as well. Okay, well, let's move forwards a bit. Now we move on to the Big Bang. You see, that's another singularity. And Stephen Hawking, I gave a talk at King's College where I described my techniques. This was in 1964. And the paper that I published, which got the Nobel Prize, was in 1965. It was published in 1965. I wrote it in 64. And Dennis Sharma suggested I would give a repeat of this in Cambridge. The movie suggests that Stephen Hawking was present at my lecture in London, which is not true. He wasn't there. But however, he was there at the talk given in Cambridge, and we had long discussions. He and George Ellis and I discussed the techniques I was using, and Stephen very quickly picked up on these and started to generalize the techniques and use them in the reverse time direction. So you could ask whether if you have a Big Bang, which was could be complicated, not nice and symmetrical as they usually have in our pictures of the universe, then might you avoid the singularity, and the Big Bang could be the result of a previous collapsing phase which bounced and came out again. And he generalized these arguments very much and had three papers in the Royal Society. Then later on we got together and proved a very general theorem which pretty well encompassed things that happened before. This is now a picture of the universe. I remember I was puzzled by the fact that people did not discuss in cosmology, in serious cosmology. I'm talking about the cosmologists, not the people who worked on general relativity theory. I'm talking about the people who actually did observational cosmology, and they looked at the universe as it is. And I asked them, I remember talking to James Peebles, who was sitting in a car about to go off to a meeting at Stevens Institute, and I went off in a different car, but before he drove off, I asked him, why is it that you cosmologists don't ever study these other complicated singularities? There are loads and loads of them, and you just concentrate on the one case where you have a very symmetrical initial state. Well, why don't you look at these other? And he looked at me and said, because the universe is not like that. And I thought, my gosh, it isn't, is it? His argument, I think, was based on the cosmic microwave background, is very uniform. And in this picture, I've drawn it as though it's very symmetrical. You'll notice at the back, there's some sort of irregularities. That's just so that the universe could be closed or open. It's a bit hard to draw a picture of the universe if it's not closed. So I pretend that it's closed for a bit and maybe it goes off to infinity around the back. But I'm not really prejudicing the issue as to whether it's actually open or closed. Now, one of the arguments that people use in cosmology is that right there, tucked in at the Big Bang, in order to see it, we need a magnifying glass, a really powerful magnifying glass, very, very powerful magnifying glass, because it's way down in sort of the first 10 to the minus 32 of a second. And what you apparently see, according to the theory, is this thing called inflation. That is another exponential expansion of the universe, which maybe would smooth the universe out. It does other things which are more technical about the cosmic microwave background. But one of the arguments people tried to make is that that Big Bang, if it had this inflationary phase, it would smooth out, and that's why you don't see all these irregularities. Now, I was not very convinced by this for the following argument. Let's imagine that time is going the other way. And so you have a model which is collapsing. And in this model, you've got all sorts of irregularities, including black holes and things forming, and they will converge on some horrendous mess at the end. Now, that is because of arguments from Stephen Hawking and Bekenstein and so on, who showed what the entropy of a black hole was. It shows that this is an extraordinarily special state not to have these black hole constituents in a collapsing model. So that a very general situation wouldn't be anything like what we see. It would be much more like this. Here we have black hole singularities all congealing in a great mess. It's much more like the sort of model that Lifshitz and Kalatnikov and Charles Misner came up with later on when their mistake was corrected, and they found very complicated solutions, which would be nothing like what we see in the Big Bang. I should say one feature of these solutions is the Weyl curvature becomes enormously large. It's absolutely huge. Now, that is a much, much more likely initial state. Why don't we have that rather than what we seem to see, namely this? Why do we have a very, very regular universe? This is the problem posed by Jim Peebles, previous Nobel Prize winner last year. And he had very good reasons to believe that it was like this from observational signals. Now, I found it very strange that we seem to see a singularity in the Big Bang. See, the arguments were sort of similar back in time and forward in time. So why do you get this very, very great difference? People used to think that these singularities would be resolved by some wonderful theory of quantum gravity, quantum mechanics modifying gravity at small scales, small sizes, when curvatures get very large. But the trouble is, if that theory explains how to get rid of the singularities in the remote future, why doesn't it apply to the Big Bang? Why do we get this very, very peculiar situation? So I just formulated a theory, wasn't much of a theory, it's just hand waving, to say that whatever quantum gravity it is, must be a very time asymmetrical model where the Weyl curvature is somehow necessarily zero in past type singularities like the Big Bang, whereas future type singularities, like the one we've just seen, they needn't be zero at all. Very, very strange kind of quantum gravity. This is all tied up with a major problem in physics, another one called the second law of thermodynamics, which tells you that the entropy increases with time. Now, entropy is a measure of randomness. And here we have in the top three pictures, the gas in a box. We have on the left-hand side the gas in a little box, and then we open the box up and the gas spreads out. So this is what you find with entropy increasing for a gas in a box. But what about stars in a huge box? They behave the other way around. That they would, if they are spread out, this represents a low entropy state. And as time progresses, these stars start to clump, and then you get black holes and things like that, where the entropy just goes shooting up. So in both pictures, top three and the bottom three, we have entropy increasing from left to right. In the top picture, it's ordinary matter, and the bottom picture, it's gravity. So gravity behaves very differently. What we do see in the early universe, indeed, is a situation like the top right and the bottom left. In other words, uniformity. What does that mean? That means high entropy in matter, and that's confirmed by the microwave background, and low entropy in the gravity, which is also confirmed by the microwave background because you see that it's uniform. But it tells us that the Big Bang was a very strange thing because it seems to be low entropy in gravity. It just singles out gravity as something special. Now, the way I started thinking about this later was due to an argument or a suggestion due to Paul Todd, my graduate student then at the time. He became a professor at Oxford, and he had this suggestion that maybe what was peculiar about the Big Bang, not just don't say the Weyl curvature is zero, but to say that it's, if you conformally stretch it out, it becomes regular. And the fact that you can squash down infinity and make that regular was something I knew about before. This picture is an Escher picture, one of his circle limits, and it describes a geometry called hyperbolic geometry. Don't worry too much about the geometry. What I'm trying to say, it's a conformal representation. You can see the eyes of the fish, they're all circles, and as you get towards the edge, they remain circles. The shapes, or the small shapes or angles, are preserved in this map. So the fish at the edge don't think they're any different from the ones in the middle. But this conformal compression is what Escher has used in this model. It's a Beltrami representation of hyperbolic geometry. And I want to try and apply the same idea to cosmology. That's something I used to do a lot, was to squash down infinity. It's very useful in talking about gravitational radiation. But the idea is to use that same argument in the opposite way to talk about the Big Bang. Now, what does conformal mean in general relativity? Well, it really just means the light cones. You see, think about the light cones. That's not quite the whole of the metric. That's 9 out of 10 components in the metric. If you want the 10th component, you have to think of these little hill-shaped things or bowl-shaped surfaces. What do they represent? They represent the ticking of clocks. Here I've got the two most famous equations of 20th century physics: Einstein's equals mc squared, Max Planck's equals h nu, nu's frequency. First one tells you energy and mass are equivalent, that's Einstein. Planck tells you energy and frequency equivalent. Put them together, this tells you that frequency and mass are equivalent. So if you have a massive particle, it has a very definite frequency given by these equations. Now, if you imagine now the world lines of massive particles, so here we have two particles traveling with a large speed, but not the speed of light. The red one intersects these bowl-shaped surfaces. That's tick number 1, tick number 2, tick number 3. The blue one intersects them, tick number 1, tick number 2, tick number 3. Particles of a definite, stable particles of definite mass make wonderful clocks. So they are perfect clocks if they have definite masses. Now but if you don't have mass, then you have photons, and photons don't even see these surfaces. So photons don't register time at all. From the origins of the photon to where it gets finally absorbed, if it does, is, as far as the photon's concerned, no time at all. So it gets right out to infinity. These light cones then are a conformal structure. They don't depend on the mass, they don't depend on the scale. The Beltrami picture, or the Escher picture, which I just showed you, is a conformal picture in space-time. It's the light cones that we're talking about now. Okay, now let's think about the whole universe. On the left-hand side, we see the model of the universe with the Big Bang, and then we see the exponential expansion, which is a feature observed again, another Nobel Prize early in the 21st century, where people discovered that there was a cosmological term in Einstein's equations, or equivalent, and this seems to show that if you squash this down, you get a finite boundary in the future. I can see my arrow in one screen, but not in the other, unfortunately. Let's try that. Here we have, at the remote future, a nice space-like boundary. The Big Bang is also space-like, so you can squash down infinity and stretch out the Big Bang. Now, I was very struck by the fact that when you do that, they look very similar to each other. You see, you might say they're very different, aren't they? Well, what about the remote future? It's very cold, very rarefied. What about the Big Bang? It's very hot and very concentrated. But if you use this conformal squashing, it not only does it make things smaller, it makes things hotter, makes the energies go up. what happens to the Big Bang. When you stretch it out, it makes things colder as well as less dense. So you get something which looks as though they're pretty similar in the remote future and the remote past. And in fact, now here's the exotic model that I put forward a few years ago, which I call conformal cyclic cosmology, is that our universe is only one eon, as I'm calling it, of an infinite, probably extended succession of these models, where our Big Bang was the conformal continuation of the remote future of a previous eon. Our remote future will be the Big Bang of the next eon. Now, I gave lectures about this a lot, thinking nobody would ever disprove me because there were no observations. And then I started worrying about this because I could think there were some observations. So let me go and see. You see, certain signals can get through. In fact, if you have something with no mass, then it can get through. You might argue, well, how about in our actual universe, why doesn't mass spoil the picture? Well, the remote future is partly because it's mainly photons running around and they don't have any mass. You have to have some other condition that the mass gradually fades out for massive particles, but I don't want to go into that for the moment. What about the Big Bang? Well, there the argument is that things are moving around so fast that the energy in particles is almost entirely in their motion and not in their mass. And so that, therefore, they are effectively massless because they're so hot. So that massless things at both ends, and if it's like a photon, it can actually get through from one side to the other. What else could get through? Well, gravitational waves. And here I have one of the ideas that I proposed, that if you have black holes in the previous eon, that's before this horizontal surface, the previous part, this is the previous eon, the red part is our eon, the purple part is the previous eon, and I have a number of black holes in a galactic cluster, supermassive black holes running into each other. So there will be several of these, and that cluster eventually becomes one big black hole, and that sits around for an awful long time. But in the process, it will emit these huge gravitational wave signals. And can you see them? Well, my colleague Vahe Gozadyan, who actually did an analysis of this, I won't go into the details of it, but I'll show you this one picture, which is an analysis where he looks for rings. You see, when you look back into the previous eon, the intersection between our past cone and the future of the purple cones is really a ring, because you need another dimension, of course, to get a sense of that. And so what Vahe did was to look at rings and look at rings which had low variance. That's the sort of signal that you might get from these colliding black holes. Low variation as you go around. But that wasn't a very strong signal. What you had to look was for at least 3 concentric such rings. As I said, you get several of them in these collisions. And this, what I want to point out, is a very remarkable signal, because he didn't look for whether the temperature was warmer or cooler, but the red ones are with warmer temperature. Those are actually the more distant ones. And the blue ones are with cooler temperature. They're closer ones. They're actually with what we call our past light cone. The red ones, you wouldn't even see the galaxies because they're outside our past light cone. You can do that because you look into the previous eon and the cone spreads out further than it does in ours. So we see these very curious, very concentrated regions. That's what's so puzzling about this picture. Whatever it is that's producing his signals is very, very, very non-uniform. And that's a great puzzle for cosmology, because people think the universe is very, very uniform. What this tells you is, on a very large scale, it's not all that uniform. And you have these very, very super duper clusters of galaxies. Well, of course, there may be another explanation. Maybe that's not the real reason. But in the model I'm proposing, in the previous eon, you have great clustering. And that will undoubtedly come through to our eon. The second observational feature was more to do with my Polish colleagues, Krzysztof Meissner, Paweł Nurowski, and Daniel Ann, who did some analysis on, another Pole originally, but Daniel Ann and the subsequent measurements which I'm talking to you now. This is another thing that Hawking predicted, is that black holes not only have entropy, but they have a temperature. And this temperature is very, 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 very cold, so you don't see much of that. But in the very remote future, when the universe expands and expands and expands, the black hole becomes the hottest thing around. and it gradually evaporates and finally evaporates away. And it just goes away maybe with what I call a pop. But whatever happens, all that radiation, because you remember the fish getting so concentrated in the picture here, everything gets so squashed down, all the radiation in the final picture gets squashed into a single point. Now here we have a picture from our paper published in the monthly notices of the Royal Astronomical Society. Daniel Ann did the analysis, detailed computer analysis. Christoph Leisner had a particular criterion for looking for these little Hawking points. You see, I'm calling them Hawking points here. In the bottom part of the picture, notice the horizontal line at the bottom. That is the crossover from one eon to the next. I'm imagining that there is a supermassive black hole finally evaporating way just underneath that crossover surface. That's what I call the Hawking point. All that energy comes pouring through, and that will come pouring through. You don't see it immediately because it takes 380,000 years before the light can ever get out. That's standard stuff. James Peeble and his colleagues, very good work that they've done on the early universe, 380,000 years. And that spreads out to what is about 8 times the diameter of a full moon. So that all that energy is spread out to 8 times the diameter of the moon. You see at the top the sort of distribution of temperatures that you have in the middle, larger increase in the temperature, and it fades off as you go to the outside. And of a size which is 8 times the diameter of the moon, or slightly less if you're not quite seeing it head on. But these we do seem to see with a confidence level of 99.98%. This is in the Planck data. This was a satellite which we originally looked at. Then we compared it with the older satellite, the WMAP data. And for the 5 strongest points in this Planck data, actually where they are is not such confidence level, but if you see them in both, that seems to be pretty strong evidence that they're genuine Hawking points. That the 5 strongest points are seen in exactly the same places in the WMAP and the Planck data. So I think they're pretty reliable. There's another one in the WMAP data, which we see also in the same place in the Planck data. So there does seem to be something there. If somebody else has another explanation, yes, I'd like to see it. But if not, it seems to me this is a pretty strong indication of something like the model that I'm putting forward. It certainly is something I hope people will consider seriously. Thank you very much.
Well, welcome to this final session, and welcome to Roger Penrose, whom I'm going to talk to for the next half hour or so. Roger, when you think of your background, your family, there were artists, there was a chess grandmaster, there was a geneticist, mathematician. Do you feel you were fed by that multivariate academic atmosphere?
I think that's undoubtedly true. I mean, my father worked in human genetics. Both my parents were medically trained, and actually they assumed that I was going to be, of me and my 2 brothers, I was the one they decided was going to follow them in the medical profession. And I believed this myself right up until I think I was in in the second year, I think, at school, and we had to decide in the last 2 years, what subjects we would do. And each one had to walk up and talk to the headmaster. And I remember as I was walking up to talk to the headmaster, I was going to be a doctor, because that's, it was sort of established I would follow my parents' professions. And then he said, well, what subjects do you want to do in your final 2 years? And I said, I'd like to do biology, chemistry, and mathematics. And he said, no, you can't do that combination. If you want to do mathematics, you can't do biology. If you want to do biology, you can't do mathematics. Make your choice. And so I said, well, mathematics, physics, and chemistry. And that was because I didn't want to lose the maths. I realized there was my medical career going down the drain. And when I got home, both my parents were really annoyed with me, because that was the end of my... Actually, they won in the end, because I had a little sister who was eventually became a doctor herself and married one as well. So they really won in the end, but not with me.
Was this something that mathematics was a thing you had to keep a grip on?
I think it was I just fell in love with it. No, I certainly had a great fondness for mathematics from quite early on. Certainly when I was 9 or something like that. I can't remember the exact age, probably earlier. But I hadn't thought of that as a career. That really came gradually. First of all, with this, when my parents had been very disappointed with it, I ditched biology. Of course, these days you could do biology and mathematics, but in those days it was very much more restricted what one's allowed to do. But later on, when I decided to do mathematics, just mathematics at University College for my undergraduate degree, my father was again very angry about that. He considered that people who just did mathematics were rather strange characters, you see. And he thought I could do other things as well as maths, so I should be more broad in what I did. But I was very determined. And I think, yes, my father had one of the lecturers, a man by the name of Kesselman, who was he was an extremely good lecturer. And I didn't know that at the time because I wasn't there yet. But he made up a special lot of test questions. I think there were 6 or 12, I can't remember quite. And they were very sort of unusual that I would have never come across before. I respected him a lot for taking all this trouble. But anyway, he made these questions up and he gave them to me and said, well, you can take as long as you like. And if you only do 1 or 2, that's fine. But then he came back later in the day and I'd done all of them. So he was quite impressed by that. So I think that was what converted my father. He allowed me to do mathematics.
Yeah. Did the melee, it wasn't a melee, it was probably an extremely well-ordered household among your relations and their friends?
Well-ordered slightly worries me when you that. It was a bit chaotic, but go on, yes.
I mean, did you get something from the artist side and from the other side and that side?
Yes, I think definitely from the artist side too.
Yeah.
Because my father was a very good artist, and he was one of 4 brothers, all of whom were, well, one of them particularly distinguished as an artist. That was Roland, who was a younger brother of his. And Roland became a big figure in the art world and surrealism, and he was familiar with all the people, with Picasso and Max Ernst and various people like that. And he then became a big figure in surrealist art in Britain. But
there's a plaque to him I pass most days.
Oh, yes, I see. Well, yes, but you see, my father's father was a professional artist. He was very skilled, extremely skilled. But he did sort of very religious pictures. He was a Quaker, and my father was also a Quaker, but not sort of religious Quaker. He was more moral Quaker, you might say, and he used to go sketching, and I sometimes went with him sketching. He was very good at sort of doing pen and ink, I think was his particular skill he had. But I did more wild things, which were not necessarily realistic, and I don't think he approved of that very much.
But the idea of drawing as part of the intellectual, or the life you led, was just there from the start.
That was very much true in my case. I don't think my brothers were so much on that side. My sister picked up on it rather, but certainly my father's side, yes. And I got a lot from him on the artistic side. I think that's true.
When you are at school, you said that you realized your mind worked in an unusual way. I'm quoting now. I thought maybe when I go to university, I'll find people who think like me, but it wasn't like that at all. When I would talk to someone about an idea, I found myself not understanding a word that they were saying. That's quite a strong remark.
Well, it was sort of that I could pick up the gist of what they were saying without really understanding the words. It was quite strange in a way. Obviously, that thought processes were very different. So when I went to university, I found that, in fact, people thought very differently from me on the whole. I think it was mainly the visual, non-visual divide, which is quite a significant one. I mean, there are lots of other differences, but primarily that one. There are people who tend to think visually and those who tend not to think visually. And I was very much on the visual side. I seem to remember when I was at university, there were only one or two people who thought very much on the visual side, one of whom was me, or well, two or three, I guess. I can remember one other particularly. But I mean, other people could do it, but that wasn't their primary way of thinking. So it was a lot. The variation in ways people thought about things was quite striking. And as I say, when somebody might be talking to me, describe some idea, and I wouldn't really follow the actual words or sentences in any detail, I'd pick up the gist of what was being said and maybe come to the conclusion that was required at the end, but not exactly following the details of what was being said to me.
Did that stay with you, or did it resolve itself in some way?
I think it stayed with me. I think, no, I think it's very true. Well, I think it was true in relativity. I think that was a distinctive feature, that I thought about the subject very much in pictures and how light rays behave and things like that, and rather than the equations. I mean, I could do the equations when needed, although even then I would have a very different way of looking at equations often. And this came about when I was a graduate student mainly, and I was supposed to be doing algebraic geometry under Hodge, William Hodge, who was a very distinguished algebraic geometer. But I don't think he was very visual in his thinking, but he gave lectures on differential geometry, and he was sort of equations all over the board, and he was a very disorganized lecturer. And I had a great deal of trouble following in detail what these things meant. And so I developed this notation where instead of having symbols, you see in the subject of differential geometry or relativity theory, you have symbols with lots of indices, and then indices at the top and indices at the bottom. And then you have to see which letter here corresponds to which letter over there. And that was much too complicated for me. So I just draw a line connecting these things. And I developed this diagrammatic way of expressing these equations. And it wasn't the way anybody else did it, but it was very helpful to me in trying to sort out the problem that he'd set me.
Did it work?
Yes, it worked. I didn't solve the problem because the problem didn't have a solution in the form that one expected. This was a striking thing, because I used this method to show that there was no solution to this problem in the most obvious way. You'd expect you're trying to construct something. You had two objects and you had to combine them together to make a third object. I won't go into the details of that. And these were very complicated algebraic expressions. The geometry is very simple. You're looking for the intersection of two geometrical figures. And that was clear to visualize what you're trying to do. But to do it algebraically, it was very, very complicated. And in order to do this, I developed this notation. And I had these pictures with lines all over the place. And I remember showing them to Hodge, my supervisor. And I don't think he followed what I was doing. He thought about it very differently. And so I at that point, I didn't show anybody for a long time. But no, it helped me sorting out this problem and to see that there was no solution in the most direct way, and you had to go indirectly to find a solution. But,
when you were still a graduate student, you developed the Penrose triangle. What was that, and why was it such a breakthrough? Not a breakthrough. Why would it please you so much?
Well, this was a complete digression from what I was doing. You see, I was at Cambridge at the time. I think it was in my second year, and there was a conference. The International Congress of Mathematicians was taking place in Amsterdam, in the Netherlands. And I and a colleague decided we'd go to this conference. And I remember I was finding a lot of it was very mysterious and difficult to understand, but they were lectures by Hermann Weyl, I remember, which was very impressive and so on. And I think I was getting on a tram at one point, and one of my lecturers, Sean Wiley, who taught me about algebraic topology, and he had in his hand a catalogue. And this was a catalogue of an exhibition that was being held in the in one of the museums in Amsterdam. And he said, you might be interested in this. It had this strange picture on the catalogue with these now famous picture, one of these, it's called Night and Day, one of the Escher pictures with birds flying, and one way it's into the night and the other way it's into the day, and the gaps between the birds become the birds on the other side. And it's very clever. And I'd never seen anything like that before. And so I went to this exhibition. It was in the Van Gogh Museum, and they had a special room full of these Escher pictures, as they thought that mathematicians would be interested in that. Escher was not famous at all at that time, and I was absolutely stunned by these things, most particularly one called Relativity, which is a picture where the force of gravity was in 3 different directions, and people were walking upstairs and at right angles to each other and that sort of thing. And it was utterly fascinating. And I went away thinking that I hadn't quite seen something of the nature which I had in mind, which is a picture which was locally consistent, but as a whole inconsistent, because there's a sort of ambiguity in the local picture about how far away it was from you. And I drew pictures with bridges and rivers and roads going different ways. And then I simplified it to this thing that people refer to now as the tribar, 3 rods, each at right angles to each other. But you can't construct locally, you can, you see. So you can have a local picture and it makes sense locally. But since the distance away from you gets inconsistent at some point, then it's an impossible figure. And I remember showing my father, and he showed it to his colleagues, and they all felt very ill looking at these things. And he then developed that into impossible buildings. He had one he called an impossible college, I remember. And then he produced a staircase which went round and round and round. And we then wrote a paper on this.
You and your father?
Sorry?
You and your father?
Yes, my father and I, that's right. And we wrote a paper on this, and we couldn't decide what the subject was and where do we send it, you see. Well, my father said, well, I happen to know the editor of the British Journal of Psychology, so I'm sure he will accept it. So we decided the subject was psychology and sent this paper to the British Journal of Psychology. It was duly accepted. And then we sent a copy to Escher. We'd acknowledged the catalogue to the museum, so the influence that Escher had. In the meantime, Escher had produced a picture of Belvedere, which does illustrate the same thing. But then he picked up on this, and he developed the staircase into the one called ascending and descending, and the triangle into the thing called waterfall.
You said of the triangle, its impossibility in its purest form. Why did that attract you? And why did you use the word purest?
Well, you see, it's really, it's not, there's no kind of elaborations to it. I mean, it really is just the impossibility. That's what I meant. What I didn't know was that there was this Swedish artist called Oscar Rottisvard who'd previously drawn a very similar thing with cubes going around like that, which I didn't know about. And there are old pictures you can find. There's a Bruegel picture called The Gallows. I think it's called a jackdaw on the gallows, is it? I'm not sure if it's jackdaw. And it's joined up differently in the top and the bottom. So it's quite deliberately. I mean, some people thought, oh, he's made a mistake. No, he didn't. It was absolutely deliberate. You can see that.
Did this attract you partly because of your interest in drawing, as well as your interest in the pure impossibilities?
I think so. Well, you see, we did other things together. That wasn't actually the first thing we did together. The first thing, as far as I can recall, was we were on a train going to Switzerland, where my mother's mother, my grandmother on my mother's side, lived, and we were going to visit her. And my father came up and he said, well, look, perhaps you could help me developing an idea, because there was the question is whether you could build a machine which would reproduce itself. And the great mathematician von Neumann had proved some theorem that with several thousands or millions of pieces, you could make this machine which would copy itself. My father he knew about this, but he wasn't very pleased with it. He thought, well, life has got come about from something simple. So there must be some simple thing which will reproduce itself. He suggested using something with gadgets which would copy themselves. And so
I did that to solve on the train on the way to Switzerland, did it?
we on the night, it was a night train, you see, and so we had bunk beds or something. And I remember I produced my solution and he produced his solution. His was better than mine. I think he appreciated mine, but I think he thought his was better. I think it was better. So we then wrote an article for Nature, which got published between us, which was called Self-Reproducing Analog or something. And it had these two little pieces, and you have them in a track, and you shake the track, and they just hit each other, and they don't combine. But if you link two together, and you can link them two ways, this way or this way. If you link them this way, then two other pairs will link up the same way. If you link them this way, then other pairs will link up that way the same way. So it was a very simple, very, very simple example of something which you could imagine some molecules doing something similar. So if life could begin with something extremely simple, not these complicated, vastly complicated things that von Neumann had introduced. So I thought the idea was a very good one, not in detail, anything like chemistry or what life would be like. Although my father then went on and developed much more complicated things he was trying to model DNA and that sort of thing. So he got a little bit, I think, too far into making these. He had a little workshop in the back garden, and he would plug away with his pedals jigsaw and make dozens and dozens of these little machines.
In 1964, you were said to have, I'm quoting, revolutionized the mathematical tools that we use to analyze properties of space-time. That's quite a mouthful. It must have been quite a... It's quite... So can you unravel that for us?
I think it's what you were saying earlier. You see, I was thinking about the subject differently from most people. You see, most people at that time, when I said that time, this was a little bit before 1964, it was when the quasars were being seen, and they were suggested that they were gravitational collapse, sort of bodies coming together and producing who knows what, and producing these very bright signals, which became known as quasars, which are extremely bright sources in the radio signals. And they were very puzzling to people. But you see, the two ways people might think about general relativity at the time were either the mathematicians who were just trying to solve the equations. And you could only solve the equations in a very simple, symmetrical, or had some very simple characteristic which you could use as a gadget to allow you to find exact solutions of the equations. I could do that sort of thing, but I wasn't a particular expert at it. The other thing people might do was put things on computers. At that time, they hadn't got very far with how modeling things that we now call black holes. But I was thinking about it in a different way, which was much more geometrical. So I had this way of trying to visualize what was going on all the time and how light rays behaved. And it was very much my style of thinking.
Were you making drawings?
Oh, absolutely. Yes, drawings all the time. But it was how light rays focus. That was the main point. And there's a really close analogy. Well, I'm glad I did physics at school, because you see, one of the things we did at school was play with optical benches. And you have an optical bench and you have these lenses and you have them at different distances and you see how they focus light and all that. And then you can have pure lenses, which are anastigmatic. So the focusing is the same in all directions. Or you can have astigmatism, where the focusing in one direction is different from the focusing in the other direction. And a purely astigmatic lens is when it's completely positive in one direction and negative in the other direction. And the curvature due to pure gravity is of that kind. So I could understand how the focusing of light rays behaved from having this experience in doing physics at school with playing with optical benches. So that was useful to me. So that's not just drawing pictures, that was having some idea of what the physics was involved. So you're not lenses now, but the kind of lens that gravity acts, how it acts on light rays, and the purely positive focusing lens, convex lens, which is positive focusing, is what matter does.
Can I just come back to the quotation, though, that somebody, another scientist said to me, the two words revolutionized the mathematical tools. Now, if you could dwell on those two revolutionizing tools for a minute or two, I'd be very grateful.
It's a hard question to answer. It's just that people weren't thinking that way. As I say, they were either looking at special solutions, which didn't tell you much about the general case. You see, there was this model of collapse to a black hole, as we would now call it, due to Oppenheimer and Snyder, which was put forward in 1939, just before the Second World War. But that was extremely symmetrical. So you could actually solve the equations. You could write down the solution on a piece of paper. And that's the Schwarzschild solution for the empty space and the Friedmann solution for where the matter was. And so you could combine these two together and simply write it down on a piece of paper, what the equations were. But that was only possible because you assume exact spherical symmetry. So it's absolutely the same all the way around a sphere. So the collapse was exactly symmetrical. But the fact that it had no pressure, nothing to stop it, if you like, the falling in matter, and the fact that it was symmetrical means that where's it got to go? There's nothing to stop it, so it meets in the center. And so the density would become infinite at the center, and so you get this infinite density, singularity, where your equations give up because things go to infinity. And what do you do? So that was the problem. But most people thought, oh, well, that's not realistic because things will be swishing around in a complicated way. They won't meet in the middle. They won't be aimed at the middle. So what do? But I didn't try to solve the equations. That was hopeless. I didn't know much about how to program computers, and so that was hopeless. But I had my way of thinking, which is to see how light rays focus and how they behaved and what. It was actually, you see, there were two problems I'd worked on before, which were helpful to this. One is one I described in my lecture, which had to do with the steady state model, which is one of the things that got me interested in doing cosmology and my friendship with Dennis Sharma, which was very important to me. The other was quite a different problem. I was working at the same time, a little bit earlier, in 1964, on a problem, a paper which I submitted to the Royal Society, which had to do with the asymptotic property of gravitational fields. So you're looking at gravitational radiation and how does it behave and what does the curvature look like in detail as you go out to infinity. And I had a way of looking at this, which meant squashing down infinity to a finite boundary. So I have in my talk this picture of the Escher picture of the fish, and they've got this boundary, circle limit boundary at the edge. But that's a particular instance of what I was doing. We squash infinity down to make it look like a nice boundary. And I was able to prove certain things. But I had one little problem, was that I needed that infinity look like a sphere. So this means that as you look out at the sky, you see the celestial sphere. Now, the opposite direction, when you're looking at the future infinity, does it necessarily have this structure of a sphere out there? Or could you have something more complicated? And so in the appendix to this paper, I thought any sensible person will just assume it's a sphere. Sure, why not? But I wasn't satisfied with that. So I thought about, well, can you prove it's a sphere? So I thought about what do light rays do when they get out? And I had a sort of argument. I think it was reasonably good in the appendix. It wasn't part of the main paper. I slaved it away, thinking I was wasting my time all the time. And I developed a lot of these techniques of looking like what is the boundary of the future of you look at a point, you look at its future, and what's the boundary look like? And how do the light rays cross over? And you don't look at that part after they've crossed, you just look at the outer boundary and what does that behave like and so on. And I developed enough of an understanding there that when I looked shortly afterwards, not very long afterwards, at this problem of gravitational collapse, and I knew about the Lifshitz-Kalatnikov paper, which seemed to show that you didn't get singularities, and I wasn't totally persuaded by that. And I remember walking in the woods and trying to think of what condition could you have to show that these singularities, I don't know why, I pretty well thought that the singularities were generic. I guess that was an intuition I had. I don't quite know why. I was toying with both ideas, that it might bounce out or it might be generally singular, but I think I thought it was probably generally singular, in opposition to what the Russians seem to believe. And but I realized you needed something non-local. Just a local condition that says things blow up because of the equations wouldn't work. Just because of the symmetry, you could blow everything up, and there's nothing of the scale to tell you that it could be local. So I was pretty persuaded it had to be something more global, the condition which was sort of more global. And then it was later on, and this story I keep telling people about, I think I had this lectureship at Birkbeck College in London, and I think I was going to my office in the neighborhood in London there, near Euston Square, and I was talking to a colleague who was an Englishman called Ivor Robinson. He actually his job was then in the US, but he was a very good person. He was one of these people very skilled at producing exact solutions. He had a real skill at doing that. I don't know what he was talking to me about. He was also skilled with verbal. And if you talk to him, he would talk in this wonderful way. The Americans loved him because he had this flowery way of talking in English. It was a beautiful skill. And so he was talking to me like this. He was doing most of the talking. And then we got to this point where we crossed the street. And as we crossed the road, he stopped talking. And we were looking at the traffic. See? And then we got to the other side, and then he talked again like this. And then after he left, I had this strange feeling of elation. And I couldn't think, what on earth is this? I must have had something during the course of the day that had cheered me up. And so I'm rather fussy about this sort of thing. So I went right through, starting from the beginning, and what did I have for breakfast, and then what go on during the day, and this, no, I can't do that. And then it came to me crossing the street. My God, that was it. I had this idea as we crossed the street of a characterization of a point of no return, which was a sort of global characterization, which is a thing I called a trapped surface. And this was a surface which, you see, as the matter falls inwards, you surround it. You're still now probably in the vacuum region outside the matter as it collapses in, and you can draw the sphere around it. And it has a curious property that if you had a flash of light, imagine an instantaneous flash of light on that sphere, that the light rays converge both ways. So if you imagine a convex surface, imagine a flash of light on that surface. On the concave side, the light rays will converge. On the convex side, they will diverge. Well, on this trapped surface, they converge on both sides. Now, actually, it sounds strange, but there's nothing wrong with that if it's only a local region. What's wrong with it is when it goes all the way around the sphere and it's converging all the way around. And I call that a trapped surface. And I realized from what I'd been doing on this other problem that I knew if you looked at the future of that region, that it had to have a boundary that was what's called compact, closed up on itself because of this focusing. And then you could see that was inconsistent with the initial surface being non-compact. And you could prove a theorem. I didn't have the best way of doing it at that time. There was a slightly better way that Charles Misner, who I learned a lot from in Princeton, and certainly a lot of things to do with the collapse. You see, one thing that I remember him telling me about was, again, this question of whether it's a local. You see, one of the things that people worried about was when stars collapse. You see, there's a lot of work. I think Dennis Lehmkuhl in his talk talked about this, the history of the collapse of black holes. And a lot of this work was on stars. And when they collapse down to this, what's called the Schwarzschild radius, the density could be enormous. And so you might say, well, we don't really know enough about densities, and so maybe that's the problem. But you see, what Charlie Misner persuading about, that's nothing to do with it. You've got a big system with lots of stars coming together, and the overall density of those stars coming together can be very small, much less than the density of air, and you would still get this condition of a trapped surface.
Did this take you to working with Stephen Hawking?
It did.
And what happened in that collaboration?
Well, you see, it was, I think it was probably December 64. I gave a talk on this. I just thought of this idea with the trapped surface, and I'm not sure whether I'd actually written the paper or not at that point. I think perhaps I had, but I gave a talk at King's College London, at which the distinguished physicist, the relativist J.L. Singh, whom I learned a lot from. He had a very geometrical way of thinking about relativity, and I learned a lot from his books on that. But he happened to be in the audience, which I was very proud of. And I gave this talk on my singularity theorem, which was the one that eventually got the Nobel Prize. I gave a talk about that. According to the film, Stephen Hawking was there with sparks coming out of his head from being inspired by this talk. He wasn't there at all. That was just fabrication. But Dennis Sharma, who was in Cambridge at the time, and he heard about this talk, and he said, well, would you like to come and give a repeat of your talk in Cambridge? And that was perhaps January in 1965, and I gave a talk there. And Stephen Hawking was in the audience, and Dennis was very keen that I would get to talk to Stephen. So he organized a private session that I had with Stephen and George Ellis, who was collaborating with Stephen on trying to find some sort of a theorem about on the Big Bang, but it was much more limited and using techniques that weren't the kind I was using. So I gave a little private talk to them on my techniques. Stephen very quickly picked up on the techniques and used my theorem in a reverse time direction in the remote, very distant. So it wasn't quite so, well, the argument was to show that my theorem could be used in the reverse time direction to show that the singularity of the Big Bang was generic too. So you could imagine a situation where the Big Bang was not the beginning, but there was a previous collapsing universe, and this swished around and did something complicated and then come swirling out again. And that's what the Big Bang was, you see. So I think that was quite a picture that was presented by people. I don't remember.
That came out of you and Stephen Hawking working together, did it?
I can't remember whether that was a prevailing view that people had. But you see, that was what Stephen worked on, yes. I mean, he was using the techniques which I'd used for the black hole collapse, but as applied to the whole universe, but now in the reverse direction. He then developed these techniques much further than I had. He used them and introduced other ideas, which, you see, I had a condition that, to describe it properly, we're being a little technical, but it's more or less saying that you can have an initial moment, if you like, where you know what's going on in space-time, and then you can evolve your equations into the future. Now, that's what's called a Cauchy surface, because the famous mathematician and philosopher Cauchy had this view that you could, well, I guess that was Laplace, but Cauchy was using the idea of developing equations into the future, and when can you do that, you see? So we call this a Cauchy surface. It's very appropriate. He considered these things. So that's the surface that you start from. When I say it's a surface, it's a three-dimensional space, a surface in space-time. So it's a moment in time, if you like. And that Cauchy surface, its evolution then gives you what happens in the universe. Now, might it be like that, or it might be that some other thing comes and joins onto your universe, you see? So you have to consider those other possibilities. And so Stephen developed ideas of what he called Cauchy horizons, which are a very important idea, coming from extending the things I did by quite a lot. And then later on, we got together. There's a curious story there too. We got together and wrote a paper together, which generalized pretty well all the techniques we'd had previously into one theorem.
Can I take you back to the Big Bang? They're saying that the Big Bang didn't start from nothing. It eased in a previous universe.
Well, that was an idea.
And can you develop that? Because that's fascinating. So there was a previous universe before ours. Was there a previous universe before that previous universe? And does it?
I think we shouldn't take this as a theory at the moment. I think it was more that people I mean, yes, there were certainly people who discussed that kind of thing.
What evidence is there for it?
Sorry?
What evidence is there for this previous universe?
No, none whatsoever. No, you see, it was more. I mean, there is now, but that's jumping ahead. At that time, there was none whatsoever. It was just, you see, there's wild speculations. People were wildly speculating about all sorts of things, you see. Yes, you see, that Einstein had this wonderful theory, and people, this was a wonderful playground for making cosmologies, you see. And this was what people were doing. When I say people, there were a lot of them mathematicians who maybe didn't know much cosmology or physics, or maybe they were cosmologists who were trying to see what the universe might be like. I mean, is it a simple model? You see, the Schwarzschild produced this early solution, which is the thing which described Oppenheimer and Snyder used, and so on. And the initial models of spherical symmetrical black holes came from that. But there were also people working on cosmology. There was this Russian mathematical physicist called Friedman, and Friedman had discussed various different kinds of global structures. The universe might be spatially closed, it might be spatially flat, it might be spatially hyperbolic. That's the kind of geometry that in my Escher picture I showed you. So these were all possibilities that people considered. And it might be there was a Big Bang, or maybe you could have a solution which didn't have a Big Bang in it, or maybe other things. There are all kinds of things. In the steady state model, you didn't have a Big Bang. And so certainly there was a lot of discussion about different things that could happen. And the point about the work that Stephen was doing there was it narrowed these down, that any of those models in which you had an initial collapse, which bounced to an expansion, and certainly you could have Friedman-type models which behaved that way, whether people took them seriously. I mean, there was one which was called the oscillating model. It was spatially closed, and it bounced like this. It had infinite number of repetitions. It was quite a well-known and studied model. And so maybe something like that was true of the universe.
So where are you in your thinking about it then? Do you think there was a previous universe to the one in which we, let's call it inhabit to inflation?
I have to think of the history here, because initially, you see, when I went to Cambridge and I got involved with Danish Sharman people, and they were all very keen on the steady state model. And so I got quite keen on that. It wasn't philosophically very nice, because the universe was there all the time, and it was there and there and there, you see. And so it was philosophically satisfying. And I felt that too. But then when the Penzias and Wilson really discovered that there was this Big Bang and evidence for an early stage of the universe in which it was extremely hot, and a microwave background, which was discovered, seemed to indicate that there was this early stage, and that really put paid to the steady state model. And I greatly respected Dennis, because when he was convinced that this was true, he says, look, I was wrong. And he went around lecturing and saying, look, now take the Big Bang seriously. There really was this initial stage where you might have to consider quantum gravity and all these things like that. Yeah, that was all going on. But you see, Stephen was really arguing against the possibility of a previous collapse bouncing into an expansion. And that was it. You could use the theorems in future directions and maybe strengthening my black hole results by maybe getting rid of the Cauchy surface condition. And sure, you could do things like that. But I think he was primarily concerned with proving that there was a Big Bang. Yes.
We've gone over our time, but they said it didn't matter. So I'm going to keep going on. They can trim it in brilliantly later. There's 2 or 3 questions. One is, well, as we're talking about beginnings, Big Bangs, you've described yourself as an atheist, but you've also said, I quote, I think I would say that the universe has a purpose. It's not there somehow by chance.
Yes, it's a bit difficult to interpret what I was saying there. I certainly didn't believe that there was some old man with a beard who waved his wand and produced our universe, or anything like that. A conscious being producing it, that didn't help at all. I mean, where did that come from, and so on? No, I didn't believe any of that. But there is something in the connection with mathematics, which is so deep in physics, The more one probes reality, the more one sees how tied up it is with mathematics. But it's not a kind of thing that you see. I guess it may have to do with my views on consciousness, and that there is something in the type of mathematics that's involved. We haven't really seen it yet in our physical theories, but we have to probe that kind of mathematics to understand what it is that governs conscious beings and things which go beyond computation and things like that. When I call it a purpose, I suppose I would say that in order to be a self-respecting universe, the thing which you might call a universe has to have beings in it that can perceive it. And it's something like that, if I could try and expand upon what I was saying. So it's not the purpose is to produce conscious beings, if you like. Maybe I could say it that way. But it's in a certain sense that it wouldn't even be a universe if there weren't conscious beings in it. Because otherwise there's been nobody to see it, if you like. I don't know, it's a little bit contorted argument.
Talking about, coming to this, talking about the about consciousness, there's a discussion going on, or a disagreement going on, about the connection, about the connection between fundamental physics and the human consciousness. On one hand, thinkers like Minsky believe that humans are machines, and there are a lot of people who gather around his case. You're in a minority, as I understand it. You say that physics are inadequate to explain the problem of consciousness. Could you give us some idea of the battle that's going on there?
You see, again, a lot of these things go back to when I was a graduate student. And an important thing was, I think I was a graduate student, I went to lectures on general relativity by Bondi and by Dirac on quantum mechanics, and a course by a man called Steen on mathematical logic, Steen, S-T-E-E-N. And he explained Gödel's theorem. And I found it completely stunning, because what he said was, if you have a system of proving results in mathematics, it's called a formal system, and you could put this in the language of computers. You say, if you could put this formal procedure on a computer, and he talked about Turing machines and all that, so I learned about all that. If you could put it on a computer, then all the things you could see. How do you know what's true in mathematics? Well, you have a proof. And what is a proof? Well, you follow certain rules, axioms and rules of procedure, perhaps. And then if you follow them correctly, that's a proof. Now, what Gödel showed was that there are certain statements that you can't prove this way. But that's not so much what struck me. What struck me was that you could see, by the way that Gödel constructed, that the particular statement he produced is true. Now, how do you see it's true? You see it's true by virtue of your belief in the formal procedures that you're following. If you're simply following these procedures, why do you trust them? Why do you know that gives you truths? Well, you understand them. Now, if you understand them, then you know not just things that you can get using them, but things that you can get using your knowledge that they're correct. And that was remarkable. That's what Gödel's theorem does. It uses your belief that these procedures give you truths, and that gives you a truth beyond the procedures.
Is it like faith?
I wouldn't say so. It's like understanding. You see, faith,
a lot of times. Never mind.
faith is a word. You see, you're sort of given this thing, and you follow it.
I interrupted.
No, and it's a good question. It's not. That's exactly what it's not like. You see, it's like understand. You understand something. Now, I thought, what does this tell us? It tells us that understanding is not computational. It's not a computation. And understanding is something you do with your consciousness. So consciousness is, it's part of consciousness as understanding. And it's that part of consciousness which is enabling you to do something which transcends a computation. And that's a view I hold, and nobody has really attacked. I mean, lots of complaints people have made endlessly, but the argument which one can produce, it's not quite the argument which I tended to concentrate on, because I got myself all wrapped up in complications. There's a much simpler argument, but it's quite clear. I was going to say it's quite clear to me, and I don't know why people don't follow me very much, that understanding, and Gödel shows you this, that understanding is something which is not a computation. And that thing is what consciousness is doing. Okay, you can make these machines which can play Go incredibly well or chess or something, but they don't understand a damn thing. They don't understand anything. They've just either they've played itself a zillion times and it's maybe pattern recognition and so on. It doesn't understand why such and such a thing works. And it's that thing which is not encapsulated without understanding.
Why do you think that your position is a minority position in this argument? But the idea that we can be analyzed like machines, provided we keep at it, as it were, has been accepted by an awful lot of people, as I understand it.
I quite understand why it's a minority position, because it means going beyond current physics. You see, you could put, and I had this view already when I was a graduate student. It goes beyond Newtonian mechanics. It goes above special relativity. It goes beyond general relativity. You can put that on a computer. You see these things at LIGO, how you get these wonderful simulations. Yes, 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 yes. What about quantum mechanics? Schrödinger equation. That's computational. But what about the amazing thing that I was staring out of the window when Dirac came to it in his first lecture? Why is it that you can't have a piece of chalk in two places at once? I didn't follow his reasoning because I wasn't listening. Then I realized it's probably I couldn't have, because there isn't a reason. That's where you have to go beyond quantum mechanics. So you see, it's a very outrageous thing I'm saying. I'm saying that what is going on in our brains, which is making us conscious, is going beyond current physics. It's not outside physics, it's outside current physics. And it's what happens. This is the position I held then and still hold, is that it's what's involved in the collapse of the wave function. Now, the collapse of the wave function is something which people brush under the carpet when they do quantum mechanics. Schrödinger drove himself almost mad by trying to understand how that can make sense. And he was saying, you know, he wished it had nothing to do with quantum mechanics if I hadn't been, you know, if he'd understood all this jumping that has to go on, you see. The jumping is you follow the Schrödinger equation, and then suddenly it jumps. It does something. It does this or this or this. That's not following the Schrödinger equation. That's what's called the collapse of the wave function. We need a theory of the collapse of the wave function. When we have this theory, or when we know how to harness theory, then maybe we can make a conscious thing. I hope I'm not alive when this happens. I'm not sure I'm in any danger of that being the case, but it's sure, it's part of physics. It's not part of current physics. It's not part of computational physics.
Why do you hope you're not alive?
I don't know. I think there's something rather awful about it. I don't know why. I think if it was there, I'd change my mind. Say yes. I'd shake its hand and say, "Nice to meet you." Sure. But there is something rather frightening about it, I think, isn't there?
About the machine, the idea of human beings
actually being conscious.
Machines, yeah.
You see, I don't think any of these machines have any consciousness whatsoever. It's not even a tiny bit. It's just nothing. Because they don't incorporate this thing which they need to incorporate. Now, if they built a device, let's not call it a machine, a device which could take advantage of, we could harness the collapse of the wave function, or what really is going on in the collapse of the wave function, then there is the potential for it to make a device which is conscious. And I certainly would accept that. They're not going to do it with computers. They're not going to do it with quantum computers. Quantum computer doesn't harness the collapse of the wave function. So sure, it's got to be something else. But no, people who will be around when these things come along will be quite happy to say, shake its hand and say, yes, okay, you take over, you're better than I am. That's all right. I have I don't mind things being better than I am, but I don't want them to claim to be conscious when they're not. That's all.
That's a wonderful place to stop. Thank you very much, Roger. That was terrific. Thank you very much indeed.
Very, very much pleasure.
Very generous in your explanations. Thank you.
Thank you.